Pardon me?
We have an hour before.
Yeah, so you'll start around 10, you have until actually 12 o'clock. So if you want, but if you want to stop at 11:45 and answer questions
Sure.
or even sooner, whatever works best for you.
Sounds good.
Is this in or not? Sorry, I was in the middle of wiping these and I got distracted.
Let's go. It's good. Yeah.
Yes, yeah, you're coming from that place, right?
Yes, yes.
Yeah.
Like, can I take a look at the camera? Usually I'm able to get both of these set up.
Yeah.
And I've been playing with this and for some reason it's not working. Are you familiar with this at all? Okay, I would love to get that back camera working so it will be on here.
Oh.
I'm not sure why that screen's not on.
Ready to go spring break.
Yes, I hear you.
The time is already summer.
But only for a couple of days, right?
Yeah.
A little tease, but I'll take it. I love winter, but I'm ready for spring.
Yeah. I don't like. Yeah.
So.
But it gives you hope.
Yeah.
It's gonna be fine.
Mhm.
Yeah, you can cut it.
I mean, it breaks the heart.
That's good.
And then, Yuanqi. Yeah.
Yeah.
Sorry, I'm waving around you.
Yeah. Perfect.
Yeah, it's just,
The water cost? Oh, yes, the water pay.
do?
I hit a bunch of buttons and I moved the camera.
Okay, so you just move the camera. Okay. Usually I don't have any issue in here, so I'm not sure what's going on.
Yeah. It's not getting it. They should be able to both cameras, right? That's the.
It usually does that cameras, but
Both.
it's okay if it does. As long as you just know. I can make this closer.
Hey, everyone. I'm doing the introduction.
Yeah, perfect. You have students who might be interested in meeting our Thursday candidate.
Sure, I can, I'm to be interested in.
So we're trying to fill a few more slots for the Thursday candidate. And one thing we can do is fill up one slot as a PhD meeting. So I was getting to do anyway.
Yeah, sure. So, yeah.
You know, students.
Yeah.
Okay.
I'll bug you about it.
Okay, yeah. And I'll bug you.
Yeah, but I just thought if you went, my students would make no sense.
Yeah, Angie students, I was gonna say, yeah.
Angie students.
Yeah. I'm trying to think, like, doesn't Ben have a project on AI science with Daniel?
That's great, yeah.
Yeah, so maybe Daniel or Ben.
So you have to share your screen, and if you can make sure your volume's on 0 and you're muted.
Sure.
Okay, and I'll do a little sound check once more people around.
And students I'm on connect.
Yeah.
Oh, you just, let me
It
show
could be
you.
a hybrid, because I want
Once
students in,
Hit
Yeah.
share
Yeah,
your
reducing
slides,
demand in
then
person.
it's supposed to pop up.
or maybe
I
you
don't
can see
know
how
why
many.
the screen's not on
in
it
person.
when it is.
Oh, I don't connect to the screen, I just.
Right, it's not.
Maybe,
Oh, there we go. It's just turned off.
so it does.
And you can move this if you need to.
Yes, students.
Okay.
No, yeah.
You're
I think
good.
so with me and Angie. That could be, like, if it's only a half hour slot, especially.
Totally up to you. Whatever works best for
This is a
you.
close.
Yes, it is. Or you can try this one.
Maybe I can move this. and try
Yes,
to-
you totally can do that.
Use secret fellowship to steer to Microsoft.
Oh, he's not.
She's gonna look at the same person that Harold is working with. And Polly Fordyce. Remember Polly?
The power doesn't seem to be working.
You get rid of the column.
Okay, then. definitely.
See that all work.
I wasn't sure that.
Yeah, she was. Yeah, I was.
That's pretty late.
Polly's the one who.
Okay.
Sure, job. She had. 1810. Somebody was saying, the weather should be a solved problem because we know now the Stokes equation, rise transfer. You could predict this, but it was insane. There's no weather. Yeah, it's like biology, we know it's binding constants, rate constants.
Yeah, my.
That's like, it's three constants, but like, once you have to read that, yeah, all those parameters, you should be able to model the whole thing.
Just
Yeah, but it's failed to even now, you get data, right? And all its fundamental processes.
I was thinking of it like this week, I mean, half my undergrads didn't respond anyway, so.
And she was this like truth with.
Not supposed to do this. I always come to it as like, happy meeting you. Must be.
Yeah, she not supposed to do this. They gave us many curves.
Something.
Yeah.
You're all set.
Yeah.
And it's enzymes, you don't understand.
Do you want a second bottle of water just in case?
And then she asked me about fluorescence work. So it's how you break it. It's sick.
Okay.
Yeah.
One.
It's right at 45, right?
Yes.
10:40, oh, yeah.
How'd you
3
feel
minutes.
about the cookie club?
Till leave the room by 12 o'clock. So
Yeah, first
ideally stop through there.
Yeah.
Thanks.
I liked it. One thing we did talk about though was like besides talking, everyone else kind of just like jumped right in
Oh yeah. I mean,
their data and stuff. So it's kind of hard to follow.
Yeah, I try to like asking a lot of questions even at talk. I guess say usually
Coming from a non-experimental background, I was
so many questions during the talk, so definitely feel free to just say like, hey, oh, do that at the end.
I thought it was really nice.
Also, if there's any a lot of answers during the talk, I will then like
It was
touch that in and say, okay, yeah.
So I should be kind of meeting Eric and Angie and didn't even know about that. Okay.
You guys try to talk together. Maybe it would make sense. I can also give you
Yeah,
one.
because he has reached out and I'm really hoping that we can, because I sent him like a draft and it's just to be determined. So I really hope we could build this. And I'm like, yeah, I do. I'm optimistic, but I'm really not yet. I'm gonna do a quick sound check for the people on Zoom.
Unexpected. I thought we were getting the other people.
Good morning. Thank you for joining us on Zoom. Can you hear us?
I thought so too.
This is a minute run all the
Give
way.
a thumbs up. Everything
More
wonderful.
like for
Thank you.
experimental.
Everyone, today we're very excited to have Yuanqi Du here. He's a PhD student in computer science at Cornell. Research focuses on developing principled and efficient probabilistic and geometric modeling methods that are inspired by and accelerate discovery in the natural sciences, spanning chemistry, physics, and biology. His work has appeared in leading machine learning venues and in scientific journals, including Nature, Nature Machine Intelligence, Nature Computational Science, and the Journal of the American Chemical Society. His research has been featured by Nature, Science, Chemistry World, Nature Computational Science, MIT News, among many others. And he's also a very passionate community builder and has organized over 20 events. So thank you, Yuanqi. Take it away.
All right. Thank you for the very kind introduction. I'm very excited to be here and share with you my work with a path toward AI-driven scientific discovery. All right. So scientific discovery underpins human healthcare and the planet's sustainability. It's really big. So let me first walk you through a general workflow for scientific discovery. So in scientific discovery, we usually start with a scientific inquiry. Say you want to kill this KP bacteria that responsible for over 3 million of deaths globally in 2019 with antimicrobial resistance. So scientific discovery is really an iterative loop. So you start with a hypothesis space. So in this case, the space are all possible small molecules to consider. And you need a verification space. So how do you test the molecule? If it actually works, can you synthesize it? Are they safe? And can they kill the bacteria? So scientific discovery then becomes the iterative loop. So the scientists pick hypothesis and validate it, get feedback, refine the hypothesis, and so on. And if you're lucky enough, we get to a new discovery by the end of this loop, a new antibiotic. However, in practice, this loop carries a steep cost. So let me show you a concrete example in drug discovery. So this is a common figure that people show in drug discovery. So today, it takes around 10 to 15 years to bring a single new drug with the cost of billions of dollars to the market. And despite there being computational approach that improving a lot of aspects of this iterative loop of searching and validating hypothesis, the cost is still high. And my research aims to compress this loop dramatically with AI. So beyond antibiotic, my work study hypothesis in chemistry, basically studying molecules of varying properties. And some of the examples of molecules I study, like small molecules that function as drugs, or antibodies and proteins, larger molecules, and also those inorganic crystals, like metal-organic framework in this example. On the verification side, I study how do we leverage molecular dynamics simulation, the de facto choice to study the macroscopic properties of molecules. For example, there's thermodynamic stabilities and kinetic rates and how fast the reaction happens, and so on. Let me give you an example of how this looks like. Let's take protein folding as a canonical example. So take an unfolded protein here, structure here. Understanding its folding process by simulation takes on the time scale of 1 femtosecond with a total time steps of 10 to the maybe 12 steps. And this can take weeks to months to run in modern clusters. And not just from protein folding. So it really spans everywhere, from ammonia synthesis that makes fertilizer accessible for world's food supply, to batteries, to reactors, to catalysis inside industrial reactors, to protein ligand bindings and all the drugs and biomolecule functions. So if we can develop, my research focus on developing accelerated molecular simulation tools by AI that really impacts all of chemistry. So on the other side, when we think about the left-hand side, we have the hypothesis space that we want to search as fast as we can, and a verification space that we want to accelerate AC validation. And on the other, in the middle, that human scientist has been controlling, steering this whole process. And the next question my research trying to answer is how do we possibly automate this process by AI? So my talk has 3 parts. We'll talk about 3 pillars of this framework. So in the first part, I want to talk about how modern generative models trained over vast and structured chemical hypothesis space can be used to flexibly design all those different kinds of molecules. So let's first take an overview on modern state-of-the-art generative models. And they are actually from physics or thermodynamics originally. So diffusion model. Diffusion models model 2 stochastic processes that transport between our data distribution and a prior distribution. A forward process take your data, say an image, and transform to remove information from it until it becomes random Gaussian noise in this case. And you have a reverse process to undo this process. So you want to reverse this process, say you have a random Gaussian noise vectors, and you want to recover the information to get back to image, clean image. This is not trivial intuitively, because you remove the information in the forward process. And the key that stores this information is so-called score function, the gradient log of the marginal density of your forward process. And with machine learning progress today, that we have very scalable way to realize this score function. So diffusion model has really achieved significant success across fields from text to image generation, video synthesis, and code generation even more recently. So my work brings diffusion model to model biomolecule systems. Let's take an example here. So you have a protein structure where the box areas are the cavity in a protein that we call a pocket. So you want a small molecule, for example, in this case, to bind to fill the space with interactions that can activate or inhibit the function of the proteins. So my work introduced one of the first framework, diffusion models, for biomolecular systems that respect their natural translational and rotational symmetries, together with several other concurrent work in protein design and protein ligand docking, if you've heard of it, that has become the de facto choice of what people use today, including AlphaFold 3. And the good thing about diffusion models are they are very rich in their mathematical structures. And I really want to highlight one thing that originated from physics and how it leads to us to use diffusion model very efficiently and in a very principled way and steer them for flexible design in the chemical hypothesis space. It's called the time reversal condition, or it's really just a generalized Bayes rule. If you think about the forward process and backward process of diffusion model, you can discretize it in time. You have a marginal P0, your data distribution, and you have forward remarkable transition kernels multiplied together, and you have back your prior distribution Gaussian and the backward remarkable transition kernels. This is the optimality condition of diffusion model that it would reach. And in continuous time, if you're familiar with this kind of process, they should look like the random equivalent derivative between the path measure, the two path measure is one almost surely. So in this talk, I won't distinguish the discrete time perspective and continuous time perspective to just give more intuition. All right, so once we've trained great diffusion models provide a very strong data prior, right? So possible labeled data, the space that we've seen, and possibly capture the implicit constraint from the data. And but after that, we really don't want to train one specialized model for one specific design choice at a time. So what we really want to do in biomolecular design is possibly that if we can throw in all of the data and during the training and as a foundation model equivalent, and then we want to use them as flexible as we want at the inference time for different design choice. Let me show you what I mean. Right? There are a couple examples I have here. So the first example is annealing. So the idea is that instead of what you want to sample from your data distribution, you want to anneal the distribution. You want to anneal to a higher temperature for more mode coverage. You can see the purple curve, or the pink curve, where you want a lower temperature. You want to maybe find only the modes where it concentrates this mass. Or you want to do some composition. You want to combine multiple models together. One example I have here is like you want to do like multi-target design, right? So you have multiple models, multiple diffusion models trained, but you don't want to train a model that with multiple designs with a very little mass, like very small support. But instead, you want to just leverage the model you already trained to design flexible as you wish. Third one, maybe the most popular one, the reward tilting. This is the same objective as if you're familiar with RLHF. So you want to maximize the reward, but at the same time to maintain the data to look like a sample from your data distribution. You have some certain preference over the space. This is related to if you want to design a molecule which optimizes certain properties. The last one, but not least, is in painting. Actually, this is a very powerful one for biomolecular design, is that you want to, in paint, because almost all the biomolecules are large compositional units, and you want to break down a subunit. You want to maintain subunit while redesign the rest. And this, I'll give you a concrete example of those, how they are being used in practice later on. But all of those distribution, the target you are trying to solve is really just some variation of your diffusion models. And the question is like, how do we do this efficiently and principally? So let's take annealing as an example. So how would you do it, right? So intuitively, if you think about it, okay, I have a complex distribution. I may just want to take whatever distribution I can take in high dimensional, and I want to just relate to it. This is called the importance sampling procedure. However, it's high dimensional, so there could be no overlap at all between the mass of the two distribution. So you cannot do this at all. The variance is exploding. Or we have a diffusion model already pre-trained, right? So a better way that we can take is that we take a sample from the diffusion models. We use a sample to relate to the target distribution. The first of all, this method has several issues. First of all, is that the likelihood is required to evaluate from a diffusion model, which is known to be expensive to evaluate the linear change variable with the emergence operator over your vector field or score function. And it can also still have errors when the two distribution has small overlaps. So my approach going back to, well, where our diffusion model came from, the nine-term thermodynamics, and take a path, it's called a path relating approach if you're familiar with it. And how does it work? So I cannot directly relating from a prior distribution, I can draw something high dimensional, and the target distribution, a new data distribution, somehow related to my diffusion model. And what do? I augment it in the time-dependent dynamics or the path space. So I augment the proposal process in point sampling with a prior distribution with whatever process that's going backward in time. And I need another process. It's called the target. The only requirement is that it started as the target process I want to relate to and going forward in time, and whatever this process is for now. I want to argue is that if you want to do importance relating, if you want to evaluate some task function on a target distribution, this is equivalent on using this pair of process to do importance sampling. Let me show you why. So in importance sampling, what we do is like we first cancels out this proposal path, right? So it's canceled out, and we can also cancel out the target path, Markov transition kernels, because we are only evaluating at x0. So the Markov transition kernels are normalized; they're canceled out. And this is indeed the right importance sampling I intend to relate my target distribution. And because this comes from importance sampling, so these two processes you can really choose arbitrary. They're unbiased. So they may affect the variance I'll talk about later, but just take it for now. And but there's still one thing is needed that I discussed before. You still need your annealed data likelihood, which you cannot get easily. We need an extra hammer for this thing. And just remember when I talk about the extended Bayes rule or the time reversal for diffusion model, I talk about one actual density ratio that we can learn from a diffusion model, right? If you assume you learned a perfect pre-trained diffusion model, you have another relationship that involves both your data distribution and the prior distribution and the learned diffusion model, P forward and P backward. And this is exactly what we need, right? So we can flip the sign to get the density ratio over the marginals to be replaced by the density ratio over the transition kernels. And this gives us everything we need to control the diffusion model in the way we like, right? Even though I just show you in the example of annealing for simplicity, but this is really generalized to all the scenario I just discussed. And in fact, this also generalized if you're familiar with today's diffusion model theory at inference time, this generalized all of them with just this simple intuition. And so now I want to go back to the practical side, right? So how do we choose FT and GT? How do we choose these two processes we do inference sampling? And intuitively, they do matter. They do matter in terms of variance, right? There are a couple of ways to do it. The most accurate way to do it is, of course, to fine-tune a new model. It's almost as getting a new diffusion model to get a new time reversal. Or you can project the space to, let's say, just care about the vectors associated with the diffusion model, the drift and the score, and let's just search the span of this two-dimensional space over time, right? Or I just do it pure heuristic. And in practice, actually, pure heuristic work out just fine. Also, there's one more thing we can do to reduce the variance. In practice, we don't want to do this long path between 0 and n. One more thing that the time reversal condition implies is that the time reversibility between any time t and t prime. Sorry. So it provides you another flexibility to reweight every step. And not only that, it also provides you an opportunity to design the intermediate marginal distribution you want to reweight, right? So you reweight every couple of steps. So instead of you just reweight at your target Q0. So now you can reweight every couple of steps. You can define QT by something you like. Maybe, hopefully, it's a better path to reduce variance and so on and so forth. All right, let me show you how this is stitched together, right? So now, giving you a problem, you want to sample from this Q0. It's related to your diffusion model, but you don't know how it's a variant of your diffusion model. How do you do it? So you choose the proposal and target process and the target intermediate marginals. And what you do is like you first sample from the prior you can sample, and you simulate the proposal process backward in time until time t. And after that, you calculate the density ratio that I just showed you with respect to the target process and your diffusion model, and you reweight. You reweight to the intermediate marginal Qt now. And you keep doing this until you reach your Q0. And this is a simple procedure to implement in practice. So now let me show you how this is really used in reality, right? So the first example, I mentioned the annealing. And let's just take the first example as a sampling from the Boltzmann distribution of this so-called analyzed dipeptide 22-atom system, which is a common benchmark in the field of molecular simulation. So the goal is to sampling from a 300 Kelvin. And you can see over these two important angles, the density plots, they have separated modes, right? So which means in high dimensionality, it's very hard to sample them. You need a very long time for your MCM, macro-chain Monte Carlo method to work. However, if you want to instead sampling from 800 Kelvin, right? So it's like when we reach temperature, the distribution becomes easier to do to sample, and they're very much connected. You can solve this very much quickly with just your favorite MCMT method. And what I propose to do is that you want to first gather samples at 800K, which is easy, and then train your diffusion model, and then do the inference time steering procedure I just described to relate the samples to 300 Kelvin, right? And for this specific example, it gets decent results and still multimodal compared to the ground truth distribution is 300K, but in this specific example, it saves 10 times more compute compared for the data collection stage. So next example, I want to show you, let's go back to this structure-based drug design. But instead of doing just structure-based drug design itself, but now I want to design a molecule that could possibly bind to 2 targets. Now I have a conditioned diffusion model, condition on different protein pocket. And I trained the same conditional diffusion model, but when it's conditioned on different protein pocket, I want to use the same model to compose this two instances conditioned on 2 different protein pockets to sample a molecule that would bind to 2 proteins. And compared to on the orange box, it's a heuristic curve to combine new diffusion model. We design much better binders with much better interactions in terms of the docking scores. That's kind of like measures the interaction between the protein and the small molecule, or because small molecule ligand part with the approach as it proposed. So you can compose 2 models. And you can also do the most natural thing to do is reward tilting. So instead of want to design a molecule that could bind to the protein, you may also want to further tilt it or improve its physicochemical properties. And here I'm showing a couple examples. You want to improve the drug likeness scores, the synthesis related scores, or both of them. Well, you still want to remain them in distribution. You still want them to remain some interactions with the protein pod. And again, the impinging one is a particular problem for biomolecule design, exactly because they are all like interaction complex or large compositional units. Here I'm showing you again the protein and small molecule ligand complex. But in reality, it could be a protein-protein complex, antibody antigen, and whatever, any biomolecule interactions. So in my work, what I did was to work on this structure-based drug design. And what I've shown is that you can actually do it very flexibly for computational chemists or computational drug discovery people to do in their daily life. You want to redesign, because you have human priors over the design space. You want to redesign a scaffold, a large structure unit of the structure, or you want to grow a fragment. Given a fragment, you grow it or maintain the interaction with the protein. Or you want to take 2 fragments and you connect them. And this is really just flexible design for all of the structure-based drug design problems. And the other work have been showing it for flexible docking or enzyme design. They're all under this framework. So in fact, this is not only thing you can do, right? You can combine multiple of them. I've only shown you a single instance of them, but you can do, for example, composition and reward tilting. And here's an example for robot navigation. So this is a maze, and you can see what the samples, these are just trajectory samples arbitrarily that does not hit a wall inside this maze. And what you want to do at the inference time is that given an entrance and an exit, you want to stitch them together by a reward function. And it's a product because you sample multiple of them from the diffusion model. And this also generalized to discrete space if you care about discrete diffusion, continuous time Markov process. And I've been applying this for ImageNet 256. This is an example of reward tilting to align the sampled image with the text prompt. And also, there are also much more application areas of this. Training a unified foundation model based on diffusion model, and then use them flexible at inference time. We've been also working on the inorganic side of the chemistry for meta-organic framework. And so you can see this meta-organic framework are constructed by the inorganic nodes, organic linkers, and the topological networks to assemble them, even in a single cell. They are really, really large compositional structures. But once you have these inorganic nodes and organic edges and how they are assembled, you can construct the third structure. And that's what we've been doing, right? So we break down this with impinging to design part of it. And we've actually synthesized a new morph in the lab, and they're actually studying how They can be used for carbon dioxide capture and so on, so forth. And on the other side, it's also very helpful for some problems like searching transition state. So here, the compositional unit are in a reaction, you have a reactant and the product and the transition states where it has to cross. And well, what I did was taking a diffusion model trained over the composition of the three, but given the reactant and product searching the transition state. And we have been achieving very good accuracy. Actually, for this example, we have very strong result with half of the predictions reach chemical accuracy. And I want to talk a little bit more about this time reversal condition. They really go beyond just what I've just talked how they should be used. It's a way, if you're familiar with variation inference or VAE in general, with one instance of it. So you may be familiar with this importance rating for the likelihood of your data. And this time reversal relation really just a generalization of this to conditional path matter instead of conditional probability. And this also generalizes the stochastic estimator for diffusion model proposed in the literature. Also, yeah, it can also go even beyond this, right? So one nice thing about diffusion model is that a consistency between the score function, the gradient of log p, and the marginal density. But people have the gradient of log p, the log probability, is encoded in this transition kernel, p forward and p backward. But in practice, people only care about the score. People only learn it with some variant of score matching. So people usually don't enforce anything on the marginal. But for example, if you want to learn a density-based model or energy-based model from the diffusion model, you would need this consistency. And this really, time reversal condition really provides a very cheap way to do this. If you are familiar with the literature, what people have been doing in this is using the PDE constraint to regularize the diffusion model learning. All right, so that was my first part. I've talked about how do we flexibly use diffusion models, steer them, and inference time for a variety of targeted design choice once we train a unified model. So now I want to move to how do we validate them. And actually, one nice thing, a beautiful bridge that connects the two parts, actually, the method I developed in the first part actually are inspired by the second part, and they have exact physical meaning in non-equivalent thermodynamics. So, okay, now I want to change to a different problem than protein floating to make it more kind of like a realistic, right? So this is a protein ligand interaction, and you have unbounded, where they are independent, they don't form any interactions. And on the right-hand side, they are bounded, right? So they have interactions between them. So I want to measure how strong the interactions are. And this is related to how strong it inhibits or activated the protein. And this is correlated with experimental values. And what measures them is the free energy. So free energy it has narrow meaning and it has a broad meaning that people use. But I'll go with its statistical formulation, which is the narrow meaning of the free energy. So this two system has two energy functions. And what do you want to, the free energy is the negative log of the normalization constant of each system. And what you want to measure is that the negative log of the free energy, the normalization constant ratio between them. And as you can see, this is a hard problem because it involves a high dimensional integral, which you cannot do. And people recasted this to a Monte Carlo problem I'm showing in a moment. So what is free energy estimation? So the way that people estimate free energy difference is leveraging on inference sampling approach called free energy perturbation, first proposed 70 years ago. So let's walk through it. So the free energy difference is the negative log of normalization constant ratio. You first expand one of them in the integral form. And what you do is you do inference sampling. You inject the constant 1 into the integral with respect to the other system. You didn't expand it. The reason why you want to do that is that you have a normalization constant for that system outside of the integral. You can move it inside because it's constant. If you do a normalized density over that system, further, you can convert it to a Monte Carlo estimator for that system. This is a very elegant that makes free energy estimation computationally possible as first place. And however, you have two distributions, U0 and UN. And whenever you do this in high dimensional, it's kind of like doing inference sampling. So the question you should ask is like, do the two distributions have overlap? And most of the time they don't. And you may just already figure out that the method I proposed to augment the path space. So how does it work? So I want to first writing the normalization constant by a normalization constant over the path. Why does it work? Because it's a similar thing as I showed you before. So the Markov transition kernels are all constant. They integrate out to 1, right? Well, only the boundary are anormalized. So you can rewrite the normalization constant by the normalization constant on the path with just the boundary anormalized, everything else normalized. And you do the same trick. So expand one of them in integral form. You inject the constant 1 into it with respect to the other one. And you use normalization constant to normalize the other one. And you have an improved sampling estimator based on the path. But the question is, how do we choose this, right? This question just came up before when I talked about how do we control the diffusion model, zero diffusion model. But here it comes up again. It turns out there's a very canonical choice that you can choose it that recovers physical quantities in that fundamental result in negative thermodynamics. So, and the way that you choose it is through this called quasi-detail balance relation. So for those of you familiar with detail balance, the difference is that you don't evaluate the same transition kernel. You have 2 different transition kernels, the red and the blue. And you rewrite things a bit. So you rewrite the negative log of the density ratio for impulse weight as something called W. This recovers the physical work discretized. This, okay, you may have heard of many people talking about physical work, but this is the narrow sense. This is not like the broad way of sense, but this is just how work defined. And then you pull everything back in. Going back to this importance sampling estimator, you recover this very fundamental result called the Yazinski equality. And the nice thing about the Yazinski equality, if we look at it, in the end, it only requires something called work. It doesn't require anything from the backward process. So you are inherently using something from the backward stochastic process, but you're not invoking it. And that's the beauty of it, right? So you don't have to know what the backward process is, but you implicitly define it through this quasi-detail balance condition. However, we can do more, right? So whenever we have this actual design choice, we can do something more. And this is just taking what I had before. So work is negative log of the impulse weight ratio. And on the right-hand side is tilde. Sorry, I forgot to mention, I used tilde to define something anormalized. We can normalize it. And after we normalize, we recover another fundamental result, came out around 2-3 years later than Yazinski equality in 2000, called the Crookes fluctuation theorem. So, and this, you don't have to worry about name, but this looks nice because right-hand side has a density ratio normalized. And in machine learning, we know how to deal with density ratios. We can inject our favorite divergence measure, maybe KL divergence, and let's try that, right? So we can take the log on both sides of the equality and take expectation. And we recover the second law of thermodynamics. What does it mean? So the expected work subtract the free energy difference, which is a constant, is equal to the KL divergence. And this is what people call the dissipation of the process. And the KL divergence is always greater or equal to 0. So this exactly recovers the second law of thermodynamics. And also, we know there's a KL, we can push it to 0. So we know how to realize a zero errors estimator. So the zero errors estimator is achieved when the KL gap is bridged or the dissipation is 0. Right. And how do we do that? Again, the time reversal condition, right? Or extended Bayes rule, if you look at it in discrete time. And this provides a bridge, so we can transfer everything we've done for diffusion model to estimate to physical chemistry simulation, to estimate free energy in this case. All right, so free energy estimation really have broad applications. We start with Gaussian mixture models, maybe more like the simple one, and to Lagrange system between confined non-interacting particles on the top and the confined Lagrange potentials clusters on the second, and the condensed phase system between coarse-grained monotonic ice on the first one, in blue, and the Lagrange solid, and we can do it for well molecules between their solvation-free energy, put them in vacuum, put them in the implicit water, or the transition-free energy, how do you translate from one state to another for the same system, and also for something in quantum field theory, 5-ball theory, how do you transport the free energy difference between the iced phase and the hot phase. And in our experiment, we recover the reference value with saving 10 times more the golden standard that people have been using, a method called M-bar. And it's the first scalable non-equivalent estimators because you can actively reduce this variance for dissipation, if you like. And the method also generalizes all commonly used estimator in optimality in what people call in the thermodynamic limit. And the previous neural method is also being a special case of our method, like a different way of estimating free energy. But in all probability, they are the same, but they completely fail for larger systems. So I'll talk about how this idea of minimizing variance in accurate estimation has helped us to translate the idea we have or the scalable tools we have built in machine learning to physical chemistry simulation. I want to tell you more about it. This doesn't stop here. It's really a new paradigm, right? For example, this is an algorithm people do sampling. Consider the top one is the distribution you want to sample. And this one is a new distribution. And you can see it's easier to go between the modes compared to the top one. This is maybe called the cold and hot temperature, right? You have multiple temperature. So instead of directly mixing the distribution on the top, which is hard, also different from the steering I've said before, you instead running MCMC on a high temperature, which is much easier to solve, and you're trying to swap samples based on some matrix testing criteria. However, this swaps have low acceptance rate when the two distributions are far away from each other. It's the same thing as inference sampling. And you can use the past perspective I just mentioned. So the variance here really relates to the acceptance rate of the swaps. Another thing I've been building is that, what if I want to, okay, now I'm finally going back to the protein folding problem, right? What if I want to measure how the system actually evolves themselves from an unfolded state to a folded state? And in this here, things change a little bit, right? So you cannot evoke diffusion model because now you have a physical dynamics you need to go through. And this goes to a generalized a class of method of diffusion model called stochastic optimal control. So you want to start with a state or distribution, and you want to reach a target state or distribution, but with a physical constraint that you have to follow this physical process. And here, the dissipation becomes the variance of sampling those events. Okay, so that was the wrap up of my second part. So I've talked about how do we build this nice bridge between the first part, steering diffusion model, with those 9 paths relating, and second part, how do we leverage this bridge to translate them to scalable estimated 9 quantities. The third part, I want to tell you a little about the automation, which has been just enabled by the current state of large language models, because they provide a very nice interface for open-ended discovery. All right, so before doing that, the first question I asked when I started thinking about this problem around 1.5 years ago, is that, are there scientific knowledge in language models before we're thinking about throwing something to them, right? So can we extract, so I framed this question as, can we extract knowledge from large language models, but still EU-defined? What does it mean? What is knowledge here, right? So how do we make sure they're non-trivial? They're not just like when we ask them, they just answer, like, is that knowledge or not? Right? So we need a better problem formulation. The problem formulation I end up with is that, how do we go through the loop of searching scientific hypothesis, or I call it sampling because it's really a probabilistic model with large language models. Here's what I did. Right? So given a hypothesis space, let's say small molecules and so on, and some oracle function, some objective that can validate how good you are doing with each of the samples you propose. And you start with the current hypothesis space, use the large language model to propose new hypotheses based on what you've seen in the past, and you use the oracle function to score them. Once you score them, you select them. You can do very flexibly, you can just keep the top K, and this becomes the evolutionary algorithm until it stops. Actually, this has been applied elsewhere. For example, in AlphaEvolve, they also mentioned our early work on this in molecular discovery. This is a very simple algorithm, but it does leverage the sampling, the probabilistic distribution of larger models, because every time you propose a batch instead of propose one. So now the problem becomes better defined. So the knowledge becomes the scientific hypothesis. I'll show you in a moment. And then the non-trivialness becomes, we have strong search method. We have strong classical method. Under a fixed budget, we want to know if they can solve it or not. So the first example, I gave large language models on small molecule. They look like this. But at that time, 2 years ago, we didn't want to test the multimodal capability of language models. So they look like really this, a long list of characters, strings, right? And what we end up with is that the method easily beat all the state-of-the-art approach. This is really a field that people have been developing since 2016, 17, with 25 baselines, with the top baseline highlighted here, based on RL, graph genetic algorithm, and the Gaussian process spatial optimization. over 23 targets that people build, right? Which is GPT-4o, which is like 2 years old model. And it boosts the performance by 30%. And this was quite non-trivial for this problem.
What's the question about the molecules? Does it bind or?
Oh, there are a lot of them. This is the PMO benchmark, the practical molecular opposition. They have some docking score. They have some rediscovery task. They have some binding affinity predicted by classical machine learning models. They also have basic QED or assisted accessibility, which they almost got. I think it's not full credit. And this is not alone, right? So I tested more. I level up the problem. Let's say, can we generate thermodynamic stable crystal structure? They look like this, but to language model, they look like that, right? So it's floating point, like point cloud file. If the closest analogy is that, and you use some quantum mechanical calculation to see, the energy below the hull, the possible of the structure below the energy E hull of the known discovered materials, and with llama 3.1, it beats. Which is also another outdated model for today. Retraining generative models specifically on that task, but at least half the result. And the third problem I throw in language model is can I even further make it more challenging and still computationally verifiable? Is called racial synthesis design. So it's really like a sequential decision problem, like mathematical proofs or so on. So you have a target molecule there. You want to break it down through a list of 10 to 20,000 action steps, and you build this direct acyclic graph, it's a DAG, until the leaf node or in another purchasable set of the precursor set with at a scale of 1 million structures. And to language model, they look like that, right? So they look like the JSON file stores a list of reactions. I'm actually trained on that. This is something we just created while I did it. And this is as time progresses, we use GPT-4o, and we can achieve, I would say, on par of the performance with Monte Carlo tree search, which is de facto choice if you think about this problem. And the search of A-star variant on this problem with the percentage measure how much of the puzzles you solve, and with a fixed time budget.
I have a quick question.
Sure.
Is it zero shot or in-context learning?
Okay, very good question. We had both. And we also had a very interesting discovery is that in-context learning helps if you give it in-context example. But it's even more shocking is that you can give it an arbitrary in-context example that looks like this format. That helps the most. And if you give it something closer to the target you want to solve, it still helps a decent amount. Yeah. But I would call it zero shot.
I have a follow-up question, but yeah.
Sure, thanks. So from all this study, I want to conclude is that a strong scientific knowledge emerges in large language models, and sampling is actually one very effective approach to extract them. So then I want to think about what's next, right? So I've done my check for language model, really knowing them, and through time they know it even better. And what should I do for automation now finally? So if you think, going back to this iterative loop, if you think about what human and the computational approach we have been building that does is that on the right-hand side. So it's basically better method to search hypothesis, given faster validation, right? But so given a very well-defined problem, given the verifiers, that's assuming we have multiple verifier, we know their preference, so it's very well-defined multi-objective optimization problem. And we search the best hypothesis, we throw in the best algorithm that we can with general model possibly, and we search the best hypothesis pops into the right-hand side. But in reality, human analyze the result and planning what to do next. Let me give you an example for this. For example, once the optimization finishes, what the human would say is the optimization result. For example, there's some caveat, there's some too many of the nitrogens, there are too bizarre behavior on the optimized molecule despite the score looks good, right? So you got to put more constraint in the optimization and so on. That's everything human do, and human need to write code as well. So, and human provides new verifiers. And now there's an opportunity to replace it, augment this with large language models today, right? So we want the language model to analyze, to search over literature, and write codes to write analysis notes, and I'll plan what to do next, and find a GitHub for it, and code it up, basically. And I realized this into a language model-based agent system I call it a scientific autonomous Go evolving agent. Saga, or because it's really evolving its scope. It's a connected by an outer loop instead of just inner loop. It's a well-defined problem that we can solve by previous computation approach. Let's take a step closer to it, right? So I'll just show you an example for antibiotic discovery that I've been talking about using as an example. Finally, I got here. So design novel antibiotic small molecules that are highly effective against this KP bacteria while maintaining good safety profiles and drug likeness related property. So the first step, we initialize this with a planner. So the planner needs to reason about, okay, what do you mean by safety profiles and drug likeness, right? So because they can have multiple definitions. And I show it here computationally, but it can really be also experimentally, but we didn't do any experiment with the experiment labs. So that align with this goal. And what are their preference, which if you want to turn the multi-objective optimization by scalarizing it to a single objective optimization problem. But that's just an example. And then pass this message to implementer, say, okay, take action, implement them in callable actions. So now I can initialize an optimization algorithm. This could be arbitrary. It could be a language model, as I showed you before, but it could be arbitrary optimization algorithm. It just searches fast solutions. It's just what we know. And then it passes back to the candidates, to the analyzers. The analyzer then write codes to analyze the trend during optimization, to search over literature if the candidates have been found, to also analyze if there are any common analog in the structures and so on, and it reports back to the planner. And the planner then decides if I've already satisfied the goal that I've just defined, or I believe that I've found, or I should just continue my loop. The nice thing about Saga is that you can see this is what human scientists do. And it naturally supports human in the loop, right? So instead of just throw a question into language model and do whatever themselves, every step here is what human basically do day to day. This is inherently supporting human in the loop. And we've tested as well. So let's take one step closer on this antibiotic discovery example. So the initial objective here is some activities against this KP bacteria, because this is a very killing bacteria that's still not solved scientifically. And we have to get data from our collaborator at Broad Institute. They have screened a large space of antibiotic activities, so we can get the data. So there's no way to get the data from internet and train that activity prediction. So that's why we do it. And also the safety and the novelty. Novelty is basically the distance from the known antibiotic that has been discovered. We don't want to rediscover it too much. And so the first step Saga does is like, okay, first reason, okay, of course, I didn't put in drug likeness because drug likeness is kind of obvious. It can figure out itself, right? So and that's actually what happened. Even before the first iteration, the planner just realized, okay, let's figure out the definition of drug likeness. Let's just initialize it. Let's say just using some QED, some very basic drug likeness score. And in the second iteration, after getting the result from the first blocks that has 5 activities it measures, 5 properties measures, and figure out it writes codes, Python codes to analyze, and to figure out there's a negative correlation between the KP activity and the drug likeness they've seen in the optimized candidates. And Saga basically realized, okay, we should change it a little bit because I don't want something like very good physicochemical property, but has no activity at all, right? Let's prioritize KP activity. So that's what it does to customize it. And I also noticed there are some metabolically liable groups in the candidates. It analyzes the candidates itself and say, okay, can we add some penalty to them? Because that happens. Either because of the space are not constrained enough, or the optimizer just figure out that way to go in there, right? So, and after the second iteration, and in the third iteration, it also noticed the top scoring molecules with motifs that are hard to synthesize. And how about we add more things to penalty like that, and to further improve the synthesizability scores. And on the quantitative side, I compare Saga against a couple of language model-based systems where they just throw in a question for a language model to figure out what to do without any specific structure and so on. So as you could imagine, Saga significantly outperforms them because it identifies crucial drug discovery property, or things could come up due to the feasibility or feasibility of the problem, or the reachability of the optimization algorithm that comes up in practice. And it strikes a much better balance between the activities and the other properties, basically. And it's actually a generalist. So this loop it's not just for antibody discovery, right? So we apply for with many collaborators and also testing some more in the lab is that nanobody design, functional DNA sequence design, inorganic materials design, and chemical process design. And and actually, I just got the news last week that we actually have been finding some new antibiotic that killed the bacteria with our collaborator in Broad Institute. All right, so let me summarize what I've talked about, if there are no questions. So, or we can edit it. So the first part, go ahead.
Sorry, if you're inviting questions.
Sure.
So what is the LLM that you use inside it? And how do you train?
Very good question.
Yeah, I'm looking at the paper here, but
we are in academia, right? So we are under-resourced. So for the optimizer, we don't use the best language model like GPT 5.2. We use like maybe GPT 4.0 or something like that, an early version. And for the planner, we thought it's very important to use the state of the art. Also, that part is not the most token consuming. I would say, as a general response, if we have a limited resource, we would just use the best models. But we were under-resourced, so we would just try to
well, that's okay. But you didn't build your own model.
No.
And you didn't use any of the fine-tuning
No,
or
not at all.
reinforcement learning methods that are provided by OpenAI.
Okay.
This is just off the shelf.
Yes.
So you engineered a prompting workflow, I guess.
Yes, everything is like that. It's search for everything algorithm. Yeah.
Yeah. Okay.
Yeah.
I just wanted to know like how the communication is happening between the different kind of agents, like for example, from the planner to the implementer, how that communication.
Yeah. So for example, for planner to implementer, planner would first create the function names.
Okay.
And with some meta description.
Okay.
And then the implementer is basically a coding agent. It has its own Python environment or so on. It can run code, it can debug, it can read your file directories and so on. Yeah.
I understand at the end you were comparing out like LLM workflows versus other LLM workflows, but when you were comparing them to the other algorithm methods, were you concerned that maybe the LLM, I guess, is doing a little bit of a jumping to conclusions over the other models where it's maybe extracting from its large data landscape, like, oh, this is the answer. Let me guess that answer, and then propose it immediately.
Very good question. In my experience, no, because in my personal experience, it's even hard to, unless you just tell it exactly this is the answer. Otherwise, it's hard to get the answer out, right? You have to do a lot of heavy lifting to inverse the language model to get it out of that answer. So that's my intuition. I have more that I can share, maybe just in general, some of the phenomenon that we've seen kind of hinted it's not what they are doing. So I'll probably hold the other question because I don't want to invite too much question. I still have the last part. So yeah, let's talk about it in there. So, okay, so to summarize, right? So the first part I talk about how today's generative models from physics actually can enable very highly unified foundation models for searching chemical hypothesis space, and you can really use them however you want with this data prior learned by diffusion model. And also I showed you like how this actually came from thermodynamics and how you going back there finally talking the big challenges there. We want to model the high dissipation process and to minimize it, actively minimizing their variance for dissipation. And the last part I talk about how human and large model co-automated discovery process can bridge, well, take the loop for a next level to, ultimately evolving its goal. All right, I also want to talk a little bit about future research. The first thing I'm very excited about this bridge between probabilistic inference and thermodynamics. And this is not new, right? So, statistics and statistical mechanics have already been building a lot of bridge. And in my second part of my talk, I've been basically relating some of the quantities, it's also not that new in physics, but in machine learning, for example, normalization constants related to free energy, importance weights related to work, and variance and dissipation, you can find not only what I just showed, but much larger categories of word translations, and also in different algorithms, you can realize, okay, what is work here, and what we are doing here, what is the dissipation here, and so on and so forth. So I think, we have been learning a lot from physics, how natural world evolves and builds themselves and for efficient compute. And so we can even build better models with physical inspiration, and also, once we figure out something computationally, even though they are really abstract, so we can translate those language back to say, okay, can we realize this in the physical world, right? So, and also scale. Otherwise, the non-equal simulation, I would say it's impossible to take too long to run, right? And in the recent work that I have been collaborating with a couple of people, that what we did was basically taking the parallel tempering algorithm that I talked about very briefly at the end of my second part, going to use it to steer diffusion models, right? So using the same framework I built in the first part. In the first part, I said you are doing this reweighting after you're going a couple of iterations and reweighting. And the thing with reweighting is self-normalizing per sample, so it has a bias if you have a finite sample. And usually in practice, people use, if you want to design protein, maybe the batch size is like 64, which is huge bias. It collapses to almost the same samples. And with parallel tempering, it's a different, they are the computational dual of each other, so you can translate this there. They're exactly equivalent in terms of theory, but just different parallelization scheme. And you can encourage diversity much, much better that if you trust me, like the other method look terrible on those generating those or just collapse to the same sample. And on the other side, I've seen, in terms of automation, I think it's very much a new opportunity for the whole world to do that, to finally do that. And human scientists takes one extreme. Let's just barely with that, do with that. And fully automated AI agents. I never defined it. I'm sorry, but we can talk about this definition. But basically, just like you don't do anything, you just throw in a prompt and does everything for you. And Saga, I think it presents a significant step towards next, because that's, when some scientists read it, scientists feel like, actually that's what we've been doing, right? To steer the goal. And but what I'm just asking, there's still a long way. This is very, the distance between these three words doesn't represent how far we need to get there. It doesn't represent how any distance measure, right? So what with the ongoing improvement of language model and so on, so what's the right level of automation we should ask? I'm building this from the left. There are people building from the right-hand side. Now I go, okay, it'd be amazing to have that, but I'm building more from the left-hand side. I say, okay, what can we reach? What can we automate step by step? And finally, that I believe we don't need, well, it'd be great if we can have autonomous lab. We have advancements from robotics, politics, or we have some people say, okay, then maybe robotics, we need to wait too long. We want to do VR, so we want to let them to see what humans have the brains, right? So I don't want to bother too much with our other colleagues on that, but just with what we already have, right? So we can already accelerate the discovery. I would be confident to say at least 10 times. And that's going to happen in the next 2-3 years. It doesn't need, well, maybe 1 to 2 years, right? And I'm also eager to tackle, what are the computational challenges we should really describe scientific discovery? Because what I show you is like, they're objective, they're evolving objective, dynamic objective. They're also like a new form of Kaggle computation, right? Instead of having a test and training set split, you also have a split between what are the objective you're optimizing versus what of the objective you're measuring, right? And those are a hard challenge. Like there's no exact computational framework to characterize them exactly, but they are very practical. And so, for example, discovery is inherent out of distribution, and machine learning is not so great known to generalize out of distribution, right? We can generalize out of distribution, but it's not like without limit. And so we really need to build a model system. I mean, there's certainly estimation. I know a lot of respect of this we're working on here, and discovery with novelty and diversity. How do we even define novelty, and or even the fundamental unobservability of the nature? Right? So we just cannot see them, even through experiment. And in the recent work, I built a paper also based on top of this, where I optimize only one objectives during training. Well, during evaluation, I evaluate on 2 or 3 objectives together. And if you only optimize one objective, even though they looks great, but for example, in the first figure, that they drops down significantly if there are no diversity to go against the observability that comes at the test time. And but if you have method that inherently leveraging sampling, the diverse distribution, they're much better, for example. And and last that I work on chemical discovery, and there are immediate. So what I do, I discover new methods, I design new reactions, I want to understand new mechanisms, how nature works, and they have immediate impact that relate to material science and drug discovery. And I think those should be realized in next 5 years. I don't want to be overestimated, overconfident or anything, because we need lab. And I've been I've been doing something with experimental collaborators in realizing the antibiotic, the nanobody we built, and also the materials. But still, I think there's a long way to go, and with a great place environment, we should be able to achieve this in the next 5 years. And this is not in a single subject, but accelerate the entire course of human scientific discovery. All right, with that, thank you everyone for coming. Now I'm happy to take any questions.
So if I may ask, I'm interested in what you think about the development of semantic communication protocols. About to the extent, especially in agentic platforms, to what extent we have a good understanding or are working towards a good understanding of what an agent understands from the questions or requests from other agents. And maybe a side question is what happens if we have foundation models and we maybe have access to their latent spaces as opposed to closed LLMs. But more importantly, where are we with semantic protocols, I guess?
Yeah, very, very good question. So regarding the semantic protocols, like interaction between agents, I think that's a rate limiting factors. How do they interact, and how do they know, how do they make decisions, right? Those are the parts so far that I'm least confident about, because I usually don't like to assume language model to be like human to make them work. So that's more like on the computational view. But that part so far, I have to treat them as human, to rely on they really learn from how human interact and so on, right? So I think I'm not seeing great, like at least in science areas that people have been tackling that problem in a great way. But I think that's the rate limiting factor for eventually how they work together. And regarding the second, on the latent space or some more interoperability, I think, yeah, that would be certainly great. But, I also feel there's a space that we need to go into. I mean, it's kind of related to this weak to strong generalization, but the large open source model, and I got a question about what model I'm using, right? So there is, I want to use the best model. That was my answer, kind of. But the question is, like, for the best models, you don't have any access to their weights and so on. They've been moving so fast. And I was also asked whether not doing fine tuning. That's all the answer. I want to use the best models. They may have the best knowledge to do the things that I want to do with science.
Thank you.
The semantics are a weak point. I'm worried about the oracles. All this is based on having a good oracle, like for antibiotic activity. I mean, I'm a little surprised that works without. Can't be too far from known chemicals. So, yeah, can you talk about the oracles?
No, yeah, totally right. Another really limiting factor, right? If we don't have good computational oracles or experiment fast enough with high throughput in the lab, it's hard to go too far, right? But my argument against that, why I'm still saying we are going to accelerate in 5 years or even 2-3 years, is that if we trust computational drug discovery, for example, structure-based drug design, the workflow has pretty decent computational workflow. If we can even if we can automate that part, that's a huge gain, right? So we also been designing, well, not me, but the community for the SARS-CoV-19 MPRO and so on that leads to drugs, right? So if we trust they are effective, that's what I'm saying. I don't want to interface with any colleagues that building new validation tools, and I'm also building them, right? So they're definitely needed. But I want to say automation is that I think of automation as a different axis. I'm not throwing let's say, give you a molecule, tell me what is free energy, find you free energy. I don't think that's going to work, right? So I'm just relying on whatever validation is already well defined out there, but I just want to automate or even let them run offline. Think about them run 24 hours a day, and to give human a reward, like a report, to get better candidates, and in the end, right? So we still have to filter, and then pass into lab, maybe at a scale of 100. In academia, maybe 10 or 20, right? So,
are you concerned in the automation process of like potential like small hallucinations that a human might miss? For example, like let's say this model creates an oracle function, right? But the oracle function code has some bug, and it's calculating the energy wrong in this small way, and it's totally screwing up the model. Is this a concern that you?
That's a very good question. I have a two sides of the answer. So on the first side, yes. And but in our test, it's not that terrible. They've been doing good, and we've been trying to trust the coding agent because they have been working very well these days. On the other side, that can be fixed by iterative loop, right? So the system has to collapse together, right? So because when you see the optimization outputs, there's an analyzer can spot in there might be some issue, something wrong. You want to have more constraints, right? So if it fails, the whole system needs to fail together. They've been just tricking humans. I say, oh, we're done, optimized. This is drug. But from my experience, it has been doing well by just driven by the high level goals on what being a drug and what are the current profiles of the candidates. So yeah, but that's a good question. You can also mitigate it through sampling. Sample a lot and just keep the good ones and keep evolving. So yeah.
Okay, there's a general question. So since we're at the university, I'm curious what you think about education. So given this progress in AI discovery, do you think education should change at undergrad level or grad level or K through 12 level? Just any thoughts on that?
Very good question. No, I think yes and no, right? So the fundamentals shouldn't change. I think, there are two parts. First, I think the frontier should definitely adapt because we want to let people, because that's more adapting to the real world strategies. And if the scientists could use coding agents greatly them on their own, I think that's great, right? So, but in the end, it boils down to you have to have people that trained understanding this, how it's doing, right? So I think the fundamentals shouldn't change. And I would say, even though I work with all of this, but all of my thoughts and it comes from the fundamental things that I've learned in universities. And right, yeah. So I think, yes and no. I think on the frontier side, they should be more open to what's going on into the real world. And on the fundamental side, we should not discard them and we should emphasize they're very, very, basic for everyone.
So I have a kind of basic question. Unfortunately, chemistry is my worst subject. But if you're talking about some of my favorite subjects, like say sampling or human AI collaboration, can you maybe tell me about what is the real discovery people have achieved here?
With AI.
With AI. And it's more like say right now we are more in the stage of reproducing human discovery that we already achieved in past, but make it faster. But we actually at some point we can make it, actual new discovery.
Yeah. Good question. First, I guess a different by field. In physics, I think you always want to do some rediscovery. Also in CS language model, we do knowledge rediscovery. But I think in chemistry, I don't think it's the case. But also, as you can see, the rediscovery and discovery has been a huge gap, right? So it's a much significant more challenging for discovery. I think in chemistry, I think more for discovery. If you ask me more, I'm not a chemist either, but maybe Jeff can comment on that. But my personal sort of view is like we face challenge and opportunity, but we have not significantly showing like ever strong evidence this whole thing how AI has been trying us and with automation that achieved, right? So we have some evidence, like people use language model to do something and throw in the lab and demonstrate some activities, but I think most of them are not strong enough. So we don't. So okay. My overall answer is like I don't think we have the strongest possible evidence for claiming that AI is accelerating this by whatever times. But it's been helping from parts per parts. For example, data-driven approach, like the co-building model, protein ligand bind, they have been helping a lot in different workflows and stuff, right? So, but I'm a little bit of more conservative. I don't want to claim that we have a consistent workflow that's from beginning or to end, like at a large degree driven by AI that solves any big problem just across science yet.
Right, but I guess maybe if I want to ask a slightly follow-up question,
Sure, yeah.
But what is the key kind of ability for a model for agent that you think you have to develop in order to do real discovery here?
Yeah, I mean, there are two parts of it, right? First, it's just automation. It's just about efficiency. Just like maybe originally you have,
But that would be like a lab technician instead of the scientist. It makes things, it do things faster, but not right.
Right. That's one part of it, right? But okay, I get your question. So the discovery is not on top of the language model. So here I'm talking about discoveries on top of how do you define where you go, right? So the decision-making process instead of the discovery is done by the search algorithm, if you would think that way. And the language model is basically constructing a feasible, well-constrained search problem for you to reach your target, if that makes sense.
Okay, I think I have a lot of questions, like, say, what is the target for scientific discovery to formulate that target?
The target is new discovery, right? So new antibiotic, yeah, so it's just anything new materials that you can validate this function. It has to be, yeah, at least to me, I think discovery first, everything follows, right? So if you find a new drug, the way you find it matters, but the drug matters more. So, yeah. So that also increased the, I kind of, maybe we can chat more offline about it. I have a lot of thought about it, but I think I know what you're kind of asking, but it's hard to a bit of expand in a couple of sentences if you are needing. Thanks.
One more question.
Sure.
Yeah, just.
Go ahead. I haven't got to go.
Yeah. So as you mentioned, like scientific discoveries about like sampling to like out of distribution or something like that. But I'm a computational material science, and I'm thinking about, for example, you mentioned about the steering and some of the traditional like accelerated sampling methods such as steering, like dynamics and some of the umbrella sampling or metadynamics. And in your vision, like how do you think like generative models whether they were replacing those traditional like sampling method based on the physical simulations, or you think it's another way?
No, I mean certainly an analogy. There are multiple angles I wanna say, but first of all, the answer is it's a synergy instead of who replace who, right? So you need both the physical ways to construct, because that's principle that from thermodynamics to mechanics, so you know what you're adding. And so on simulation side, I think it's synergy. And on the other side, I want to highlight, umbrella sampling, metadynamics, they're beautiful in terms of math. Like you can translate them, like umbrella sampling, just like you're doing important sampling with a mixture models, right? So and the metadynamics is just like it holds the potential to solve the exploration issue. So in sampling, the big thing is exploration. And metadynamics, okay, for those of you who are not familiar with metadynamics, metadynamics works by, you have a multimodal distribution. Once you can spend a lot of time in one mode, but once you spend, so you have a function to pulling water into that big hole, and you spend time there. And once you spend enough time, and just get you out to flowing out to other. Yeah, so that's what I'm saying. Like both on the ideas, they're great. And even for parallel tampering, I discussed a bit of today, is that there'll be really less focused in the statistics and other sampling community, but they are the de facto choice of molecular dynamics. There's almost no other choice. So I think there are a lot of space to study those. And yeah, I don't think anyone will be replaced. Yeah.
Okay,
I think
just a quick note that I don't know if people know about dual use, but your technology is dual use. Have you heard that term?
Yeah, kind of.
Do you have any thoughts on that, or?
Or like using transfer like both sides?
So this is super powerful, and you're talking about chemical stuff. So it's really easy to switch that from beneficial uses to harmful uses. I just think that should just be said in the room here before we finish, just so people are aware. We could talk about it later, but.
Okay.
On that happy note, we'll.
It's scary as we get powerful.
Oh yeah. Oh yeah. I did this. Yeah, thank you everyone.